Hello everyone. So thank you for coming for this university session on TensorFlow and deep learning. You're brave to come and spend 3 hours here with me talking about neural networks, TensorFlow, and all the nice things we can do with them. So let us start. And yes, maybe like this. Can you still hear me okay? Yes, even in the back, everybody hears me? Perfect. So let's go. I have quite a few things for you today. Of course, we won't cover everything there is to cover in neural networks and deep learning in this university session. But basically, I would like to walk you through two canonical examples. One, which we'll do in this first session, which is handwritten digit recognition. And then in the second part of the session, we will dive into recurrent neural networks. What I hope is that with this little dive in let's say, 3 different types of neural networks, you will have enough information to then go on your own and read neural network blogs, read the scientific papers, and actually parse through the not always useful mathematics and formalism and understand the architectures that are being explained. So let's dive right in. This is a very classical data set. It's been around for around, let's say, 20 years. If you go to the website, to the MNIST website, you will see that people have been working on this. You have 20 years of scientific papers published. And we will summarize this, all the progress that has been made in this field in about 45 minutes. So let's start. Let's start and let's build the simplest possible neural network for recognizing those handwritten digits. Just before you go, who was in the TensorFlow session yesterday, the code lab? Okay, a few people. So I hope you don't get bored in the first 45 minutes because you'll have seen this already. But we'll kick it into overdrive right after that. So stay around. And also, who has some experience with neural networks and deep learning? A couple of people. All right. So please feel free to intervene, feel free to help, feel free to add additional information. I don't pretend to know everything. But if you don't have any experience with neural networks, I will make my best to start the explanations from the very bottom and build it all the way to the top. So yes, let's build it. This is the simplest neural network you can imagine for recognizing those handwritten digits. So just 10 neurons. Our images, they come as 28 by 28 pixel images. The first thing we do is that we flatten all those pixels into one long vector, 784 pixel vector. And that is what we will use as our inputs. And now our 10 neurons, the 10 circles here, they will always be doing the same thing. A neuron does a weighted sum of all of its inputs, adds a constant, which we call the bias, and then feeds this sum through an activation function. There will be several activation functions mentioned today. The one thing they share in common is that they are nonlinear. So that's all there is to it. A weighted sum of inputs plus a constant fed through a nonlinear activation function. And now we have those 10 neurons. Why 10? Because we are classifying digits from 0 to 9. And our hope is that if we choose the weights of the weighted sums correctly and the biases correctly, one of those 10 neurons will have a very strong output telling us that this is actually an 8 that has been recognized here. So which activation function are we going to use? As I said, we'll see several, but for classification problems, the wise minds that came before us tell us that softmax is actually a very good activation function. And it's extremely easy to use as well. Softmax is simply the exponential of the sums you get in the input. And then once you have taken your 10 exponentials, you normalize this vector of 10 elements. Okay? So the full process is each neuron does a weighted sum of its inputs plus bias, elevates this to the exponential, and once you've done this 10 times, you normalize this vector of 10 elements. Normalize using which norm, whichever you want. It really doesn't matter. L1, L2, Euclidean norm. The usual norm used in softmax is L1, so the sum of absolute values, but that doesn't matter. So now we need to formalize this as a formula using a matrix multiply. But actually, I'll do something slightly more. Let me formalize this not just for one image, but immediately for a batch of 100 images. So down there, I have a matrix with my 100 images. There is one image per line, all the pixels flattened in one line, okay? And on the top there, I have my weights matrix. So let's go. Using the first column of weights of the weights matrix, I do a weighted sum of all the pixels of my first image. First weighted sum. Then using the second column of weights, in the same way, I do a weighted sum of all the pixels of the first image. And using the third column of weights and so on. So here I have my 10 weighted sums for my 10 neurons. The last thing is to add the biases. These, again, are just constants. It's additional degrees of freedom, just as those weights are degrees of freedom of the system. So I add one bias per weighted sum. And if I continue this matrix multiply, I will actually repeat this exact same operation for the second image, and then for the third image, and so on until the last image. So now I would like to write this as a simple formula, which you have on top there, but I still have a problem with the plus there. So x times w, that's the operation I just did, that works fine. Now the plus doesn't quite work, does it? X times w, look at the size of this matrix, the resulting matrix. It's 100 lines per 10 columns. Can I add a vector of 10 elements to this? Well, obviously not. The sizes, they don't work. But never mind, let's redefine what plus is. Okay, that's a simple solution. And actually, it's a very standard solution. It's the way plus is defined in Python and NumPy, which is the scientific computation library in Python. By the way, who has some experience with Python and NumPy here? Okay, like half the people. Okay. So broadcasting plus, the rule is if you are trying to add two things and the size don't match, don't give up. Just replicate the small thing as much as possible until the sizes match. And it just so happens that that is exactly what we want to do here. We have only 10 neurons, one bias per neuron, so only 10 biases. So this vector of 10 biases, we want to add it on each line. Okay? So broadcasting plus is exactly what we want, and we can write our formula like this. And we obtain the basic formula for one layer of a neural network. So let's recap. In X, we have a batch of images. 100 images, one per line, all the pixels flattened into a linear vector of 784 pixels. In W, we have our weights, and X times W are the weighted sums for each neuron and each image. We add the biases and then feed this through the softmax activation function line by line. So this line by line takes the sums, elevates them to the exponential, and normalizes this line of 10 elements. Next line, same thing, next line, next line, next line. In the end, we obtain for each image 10 values. Those 10, the 10 outputs of our 10 neurons. Those 10 values are normalized, they are between 0 and 1, so we can interpret them as probabilities. And those 10 values will actually be the predictions from our system. We are hoping that one of them will be big, telling us that this number that was seen in the inputs was actually a 3 or a 5 or a 7. So, this will only work if weights and biases are good. But what is good? So we have to define good. And then once we define good, we'll be ready to train this system to determine our weights and biases. By the way, this is how you would write it in Python using TensorFlow. So I hope this is not too surprising from here to here. TensorFlow has this quite useful NN neural network library, which contains a host of functions which are used in neural networks. All right, so how do we assess the quality of our predictions? So we will be training the system. So we have a batch of images, handwritten digits, for which we have the correct labels. We know what they are. And we have this system that, when you give it an image, gives you predictions. So what we actually want is to compute the distance between what the system predicts and what we know to be true. Here is how our predictions are going to look like. 10 numbers between 0 and 1, hopefully one of them quite strong. So all we have to do is encode our known labels in a similar format, basically all zeros and just 1 1 here in the 6th position because this was a 6. And in this format, now it's trivial to compute a distance between those two vectors. So what distance? Again, any distance you like, that's fine. L2, the Euclidean distance, will work. L1 will work. Any distance will work. But for classification problems, there is one distance that works just a slightly tiny bit better. There are good reasons for that you can look it up on the internet. And that distance is the cross entropy. So how is the cross entropy computed? Very simply, it's the values on the top multiplied by the logarithms of the values on the bottom, element by element, and then you sum all these across the whole vector. Why do we add a minus sign? Yeah, anybody has an idea? Minus sign because? Oh, thank you, that's so kind. Well, the values are between 0 and 1, so a logarithm of that is always negative. That's why we add a minus sign. And we have a distance. We have a distance between what our network predicts and what we know to be true. So now that we have this distance, we can actually try to minimize it. And this will be our goal during training: find the weights and biases in the system that minimize the distance between what the system predicts and what we know to be true. So let's go. Let's try to train this system. Demo time. Run. Here we go. So, here on... Oh, thank you. That was nice. What's going on? The demo gods are not with me today. Let's go again. I hope I don't have a process lying around somewhere. No, not this one. Okay, bad demagogues indeed. So, let me solve this issue really quick. this Mr. needs to re-index, and we should be good to go. All right. So here you have the 100 training digits, which are being fed into the system 100 images at a time. You see, I put on a white background those that have already been correctly recognized by the system, and on the red background on the top, those that are still missed. What you see on the bottom here are test digits. So when you train to assess the quality of the final result on real-world data, well, you don't use real-world data, but you have to use data that the system has not seen during training. It would be cheating otherwise. So here I have 10,000 test digits. You only see 1,000 of them, so you have to imagine 9 additional screens of digits down below. But again, I sorted to the top on a red background all the digits that are incorrectly recognized by this system, and you have on a white background on the bottom all the correctly recognized ones. With a little scale on the side which tells you actually the percentage of correctly recognized images out of those 10,000 test digits. So the first thing you see is that even with this very, very simplistic model, just 10 neurons, we are already correctly categorizing 92% of our images. That's not so bad. On the top, we have our loss function. So computed both on the test digits and the training digits, well, you see it's going down. So something is working there to make the loss function go down. The accuracy, that is simply the percentage of correctly recognized digits. So it goes up to 0.92 over there. And here you see weights and biases. So these diagrams, actually the bands, are percentiles. So don't worry about that. Just remember that the full range of all the bands is where 100% of all the values are. So what you see here is that biases and weights in the system, they started at 0, and they started changing during the training process. And they ended up the weights between -1 and 1, and biases somewhere between -20. These two diagrams are just useful to see that things are moving, and it's good to keep an eye on them just in case you see the weights and biases shooting off in the hundreds or thousands. That would mean that your system is not converging. All right, so that's what the training process is all about. You throw known digits at the system with known labels. You compute the difference between what the system predicts and what you know to be true, and you try to adjust the weights and biases in such a way as to make this distance smaller and smaller. So let's see how to do that in practice. And in TensorFlow. So now we dive into TensorFlow code. In TensorFlow, you have to define, first of all, placeholders and variables. So variables are all the degrees of freedom of your system. It's all the things that you want TensorFlow to determine for you. In our case, our weights and biases. Then, when you train the system, you will be throwing data at it. So you also need something to put the data in. For that, in TensorFlow, you define a placeholder. Here, I have a placeholder for my images. So let's look at the shape of this placeholder. We're using tensors, which are basically multidimensional matrices, and they have shapes which indicate on each dimensions how many values you can store. So this one, starting from the left, none, will be the number of images in this batch. At this time, it's not known, so it's just none, but when you provide the batch of images, there will be a certain number of images in there. And then our images are 28 by 28 pixel images, and the last dimension, which is 1, is the number of values per pixel. So here we use grayscale images, 1 value per pixel. The 1 is not useful. but I put it in there just in case you want to use color images. That is where the 3 would go for RGB. So placeholders, variables. And then we're ready to go. So the first line on top is our model. That is the one-line model that we have determined previously. The only difference you see is the reshape statement there in the middle. So remember, our images, they come as 28 by 28 pixel images, but we want them as one long vector, all the pixels flattened in a line. That is what reshape does. And in the shape there, the -1 in the shape simply means there is only one solution, figure it out. Okay? So the -1 will end up being the number of images in this batch. Apart from that, it's what we have seen. It's matrix multiply of x by the weights plus the biases fed through the softmax activation function. Then I define a second placeholder for my known labels. And now I have the known labels, I have my predictions, I'm ready to compute my loss function, my cross entropy. So that's what I do in the middle line. It's an element-wise multiply of elements of the known labels multiplied by the logarithm of elements of my predictions, and then a reduced sum does a sum across the vector of all of that. So I have my loss. The last thing to do, the 2 lines on the bottom, I won't get into the details, that just computes the percentage of correctly recognized images. You can parse that on your own if you want. It's just for display. All right, and now we go into the heart of what TensorFlow provides you as a tool. So we pick an optimizer. There is a full library of them, but gradient descent optimizer is the simplest optimizer in the library. And we tell this optimizer, well, please, can you minimize our cross entropy? So what is going to happen here? Let's look at this cross entropy. What does it depend on? You see, so apart from depending obviously on the training labels and training images, it also depends on weights and biases. So to minimize it, the process is first to compute the gradient of this function. The gradient is the vector of all the partial derivatives of this function relatively to all the weights and all the biases in the system. So first of all, little technicality. How many weights and biases do we have? Just the weights, 784 by 10. That's 8,000. So we have roughly 8,000 of those weights and biases. Our gradient vector will have roughly 8,000 partial derivative components. So thank you, TensorFlow, for computing this for us. By hand, it's a bit cumbersome. And actually, when TensorFlow does this, it is a formal derivation. It's not a numerical derivation, it's a formal derivation. TensorFlow knows exactly what you have defined as computation steps and does a formal derivation of that to compute these gradients. Let's skip over this. We have a tool that does it. Usually, in a neural network class, you spend the next hour or two on computing that gradient. We can skip that. Yes? No, of course not. All the weights in the whole weights matrix are all different. Yes, the very good question. The gentleman was asking if the weights were the same in some of those columns, but no, all the weights are different. Each neuron, in our 10 neurons, each neuron does a weighted sum of all of its inputs using its own weights. Each neuron has its own weights. So each column of weights here is different. Each column of weights corresponds to one neuron. And but the columns, but within the one column, they're the same. Sorry? In one column, the weights are the same. No, there is one weight per input value. Basically, one weight per pixel of the input image. And it's possibly different. So all these W's in this 10 by 784 matrix, so those 8,000, roughly 8,000 weights, they're all different. It's a very good question because we'll get to convolutional networks in a moment, and there the weights are shared in some ways. So, who knows why a gradient is useful? Where does it point? Come on. Who knows in which direction does the gradient point? Sorry?
Down toward the optima?
Almost. It points up, but we add a minus sign, and yes, it points down. Exactly, exactly. Which is fantastic because that's what we want. We want to go where the loss is minimal. So we now have an arrow telling us this is where to go. We just have to follow it. So let's recap. In which space are we? We are in the space of weights and biases. And we have this arrow telling us, well, if you go in this direction, going in this direction in this space means modifying the weights and biases by some fraction of this vector. If you go into this direction, your loss is smaller in that direction. Well, that's fantastic. That's exactly what we wanted. So this will be our training loop. The training loop is compute the gradient on the current batch of images and labels, add a little fraction of this gradient to our weights and biases to make them evolve, and start over with a new batch of images and labels. What is this learning rate there? Well, that's the little fraction of the gradient that you will be adding. So why not add a full gradient? That's simply because that would be going too fast. To take a metaphor, imagine you're in the mountains on a peak top, you want to reach the bottom of the valley. So we are quite good at computing gradients. We have sensors for that, we know what down is. But if you have 7-league boots and you do jumps of 7 leagues, you will just be jumping from one side of the valley to the other. You're never going to reach the bottom, even if you know where bottom is. So you have to make small steps to actually reach the bottom. That's the learning rate here. Once you compute the gradient, you multiply it by this, which gives you a little fraction of the gradient, and this little fraction, those are the deltas that you will add to your weights and biases. All right, so let's write this training loop. But before, I have one more thing to explain. TensorFlow has a deferred execution model. So everything we've done so far using tf.something statements, those statements, when executed in Python, they don't produce results. They produce a computation graph in memory. They just define a computation graph. So why is that useful? Well, first of all, I told you that TensorFlow does a formal derivation to compute the gradient, so it has to know the formula for your loss, the complete compute graph, to be able to do a formal derivation on it. And the second thing, also very useful, is that TensorFlow was built primarily for distributed computing. So the fact that the graph is known in memory helps a lot when distributing those computations to multiple servers. But for us, it means that we have to do something more to actually get those graph nodes executed and get values out of them. And that is to define a session, a TensorFlow session, and then anytime you want to compute something, you have to go session.run and a node of your computation graph, plus a feed dictionary in which you feed in all the missing data for which, up to now, you have defined placeholders. So here, look at the syntax for filling the placeholders. The feed dictionary actually is called train data. It's x, colon, batch, and so on. So those batches of images, I use a little utility to give me 100 images and labels at a time. And then the syntax of the feed dictionary, in this syntax, the keys x and y underscore, those are exactly what I have defined as placeholders before. So that's the link to placeholders. Here I feed them and execute my train step. What is the train step? Well, that's what we had on the previous slide. Train step is what you obtain when you ask this optimizer to optimize your loss function. So train step is actually the step that computes the gradient, derives from that the deltas to apply to your weights and biases, and updates the weights and biases. The train step is what makes your weights and biases move in the right direction. And so this is the full the training loop. Load 100 images and labels, execute the train step, which computes the gradient and updates your weights and biases, start over again. That's it. All the rest, what you see on the screen, is just for display. So that has nothing to do with the training, it's just so that we get our pretty curves on the screen. We compute the accuracy, the percentage of correctly recognized images, and cross-entropy, both on our 100 training images and also on our 10,000 test images, so that we can display our red and blue curves here. Obviously, don't do the test computation on every iteration. Put a test there somewhere saying every 100, every 1,000 iterations, because processing those 10,000 images is quite expensive. Okay, so that's all there is to it. Here is the full code for training this initial neural network. Let's recap. So placeholders and variables for all the degrees of freedom of the system, everything that you want TensorFlow to determine through training. That is weights and biases here. Placeholders for all the training data, our images, our known labels. Now we can compute the model. That's a one-liner which produces predictions.
Sorry.
Yes.
I'm a little bit confused about the train step.
Yes.
And the link with the gradient. So,
Okay.
the way I see it is that you randomize a little bit the weights compared to what you had before.
Initially, you randomize them, yes. At the very beginning, just at iteration 0.
So what's this gradient? How is it computed? I thought it was computed from a before, after, it's better, so the gradient should be that.
So the gradient, you have your loss function, which is a function that depends on training data, your 100 images and labels, the weights and the biases. It's a complicated function, but it has those 4 parameters. It depends on weights and biases, which means you can derive it relatively to weights and biases. You obtain a gradient. A gradient is for the current batch of weights, and, for images and labels. This gradient is an arrow in the space of weights and biases, pointing in a direction where it is known that the loss will be smaller. So you take a little step in that direction, and that's it. Then you... It's yeah. The gradient, formally, it's the vector where each element is the partial derivative of your function relatively to one weight. And the next element is relatively to the next weight, and the next element is relatively to the next weight. So we have 8,000 of those. Okay? Thank you for the question. If it wasn't clear for you, I'm pretty sure it wasn't clear for everyone. Yes, we were at the model, and the model gives us predictions. And now we can compute the distance between those predictions and the known labels. That is the cross entropy over there. The 2 lines at the bottom, just the computation of the percentage of correctly recognized images. At the top there, we pick an optimizer. We ask it to minimize our loss function. That gives us a training step. And we can now launch a training loop. In this training loop, we load 100 images and labels and execute the training step, which will actually make our weights and biases evolve. And that's how we train the system. All right. So this gives us a little recap. What we have in our neural network soup right now. Softmax, we've seen, is a good activation function for the last, in our case, the unique layer in a classification problem. Cross entropy, a good loss function for classification problems. And this mini batching technique of training 100 images at a time, so actually nobody asked why we are doing this. We could be training one image at a time, of course, that works as well. Two reasons why we do it 100 images at a time. The first one, very technical one, is that we want to be running this on GPUs. I actually have a GPU here that is running this. Not really needed for this little example, but for further examples, this could be nice. And with mini batching, you actually use bigger matrices, and bigger matrices are easier to optimize on GPUs. So very down-to-earth reason. And the second reason is that if you compute the gradient on just one image, well, from one image to the next, there can be a bit of variation in where this gradient points. So you will get to a local minimum, but you might get there by widening ways. If you do this on 100 images at a time, you already get a consensus over 100 images of what is the best global direction. So it's a little bit more stable to do it 100 images at a time. Okay, so using this 10 neuron, one layer network, we get 92% accuracy. Is that good? Who thinks this is good? This is god-awful, yes, of course. Just imagine you're the post office, you want to use this to recognize postcodes. Well, missing 8 digits out of every batch of 100, it's terrible, it's terrible. So, we have to do better. And of course, deep learning is fashionable, so let's go deep and add layers. It's actually fairly easy to add layers to a neural network. Look at the first layer of neurons. Each neuron does a weighted sum of all the pixels of the image. So just as easily, you can add a second layer where each neuron does a weighted sum of all the outputs of the previous layer. That's it. That's how you stack them high. Just one thing, we keep softmax as the activation function in the last layer because it produces nicely normalized values between 0 and 1, which we can interpret as probabilities. We like that. We are in a classification problem. But for the intermediate layers, you want a different activation function. And actually, the most popular one is the sigmoid, which is simply a continuous function going from 0 to 1. So, what do we have to change to get this? So first of all, you need a weights matrix and a bias vector per layer. We just had 1 before, now we have 5 or whatever. You need 1 weights matrix, 1 bias vector per layer. It is also good practice to, as you pointed out, to initialize those weights to be small random values at the beginning. So that's what I do here. Truncated normal is just a complicated way of saying random. And now that I have my weights and biases for all the layers, this is what my model becomes. So hopefully you recognize the first line. It's the formula for a one layer of a neural network that we have seen before. The only difference is that this time is using sigmoid as the activation function. And the second line, actually, instead of using x, the images, as its inputs, now uses y1, the output of the first line. And so on. y2, the output of the second line, goes into the input of the third line, and so on, until the last line, where the only difference is that the activation function is softmax, because we want to get predictions. So that's it. Those are all the changes I need to make to my code. Replace my model, one-line model, with this. And of course, I need to define the additional weights and biases that these additional layers require. All right, so let's run this. But actually, before we run it, we will do one more little change. I just lied to you, telling you that the sigmoid is the most popular activation function. It used to be, it's not anymore. people have invented the Relu. What is that? It's even simpler. That's a Relu. It's just 0 for all negative values and identity for all positive values. And surprisingly, it works better. So especially in very deep neural networks, this activation function is a lot easier to work with. So why? The real reason why, I'm not lying to you anymore. The real reason why, we don't know. People tried it, works better, yeah, success. I'm honest. You will find plenty of papers full of equations which are after-the-fact explanations. Now, what do they explain? There still is a reason. So basically, the problem with this function is that on the sides, it's flat. And flat means a gradient of 0. You use the gradient to move forward. So having a function that has a gradient of 0 in some regions might not be ideal. And this is actually a problem that bites really hard when you have multiple layers. You stack those high, so those 0 gradient regions can actually combine and get you into what is called a vanishing gradient problem, where the gradient you compute on your neural network has very, very small values. And since that is what you use to go forward, well, you stop, you don't go forward anymore. And the Relu doesn't have this problem because, well, you see, at least on the right side, it's not bound, it's not flat. So less vanishing gradients problem here. Actually, the second explanation is that the guys who invented this, they were inspired by biology. And it used to be the consensus among biologists that the physical, biological neurons in our heads, they behave like the sigmoid. And apparently, the latest research seems to indicate that biological neurons behave more like this. So when they are not stimulated, they output 0. When they start being stimulated above a certain threshold, they start outputting not 1, but something that is proportional to the amount of stimulation, like this. So that was where the inspiration was, but then once inspired, people tried it, worked better, success. Actually here, I'm showing you only the 300 first iterations, so really the very beginning of the training. This is what you get with sigmoids. This is what you get with Relus. So you see it starts faster, and we will see that it actually ends up higher as well. In this case, this is such a simple model that we can perfectly well training with sigmoids as well. It works. It works just slightly, a little bit better with Relus. So let's use those Relus, and let's push the training to 10,000 iterations, and this is what we get. 98% accuracy. So first of all, oh yeah, this is good. 98%. We just jumped from 92% accuracy to 98% accuracy. But still, I don't really like the appearance of these curves. Look how noisy this is. Look at the test accuracy, the red curve over there. It's jumping up and down by a full percent. That's not right. So when you see this, it clearly means that you're going too fast. This is how it manifests itself when you're jumping from one side of the valley to the other without really reaching the bottom. So here you know you have to go slower. But just lowering the learning rate by a factor of 10, that will slow down your learning by a factor of 10. Not really desirable. So actually the right approach is to start fast and then slowly decay your learning rate to get slow towards the end. That sounds like, so trivial. Why am I even mentioning this? But look at the results. It's spectacular. So this is what you get with a fixed learning rate of 3 10 minus 3. And this is what you get with the same learning rate at the beginning, but you decay it gradually towards 110 minus 4 at the end. All the noise is gone. And look at the test accuracy. We are now stable above 98% accuracy, not just peaking up there sometimes. We are stable above 98% accuracy. And look at the training accuracy. So the blue curve over there. In the last 2,000 iterations, it is stuck at 100%. Actually, you can't see it on the graph because the 100 is not represented. But it's stuck at 100%. So across 2,000 iterations, at least on the training data, here for the first time, this neural network is not making a single mistake in identifying those training digits. Remember, how many training digits do we have? 60,000. How many do we process per iteration? 100. How many iterations to process them all? 600. That's what we called an epoch. An epoch is when you have seen all of your training data once. So an epoch is 600 iterations. Here, across at least 2 epochs, we have for the first time identified perfectly correctly all of our training images. It doesn't mean that we are doing perfect on the test images. Of course not. But at least on the training images, for the first time here, we are perfect. So I'm quite happy with the noise levels and the accuracy which I obtained. But look at this curve. It's really weird, isn't it? That's the loss computed on training data and on test data. So on training data, it goes down. Well, that's to be expected, you know. We are minimizing actively. We have an algorithm that actively minimizes the training loss on our training images. So it works, and the training loss is going down. But look at the test loss. So that's the same loss computed on the test images. At first it goes down, and then there is a disconnect. Well, first of all, this is not completely unexpected. Remember, our optimization algorithm never ever sees the test images. It's completely alien to those test images. All the work it does is on the training images. It doesn't even know there are test images out there. So it's not completely... So the fact that the work being done on the training images does have a positive effect on real-world performance and the test images is a kind of a byproduct of neural networks. And, well, it works when it works, and sometimes it stops working. This is what we see here. At one point, there is this disconnect, and the work we are doing to minimize the loss on the training digits no longer has a positive effect on real-world performance. So this is to be expected, but what can be worrying is the size of this gap. When you look up literature, usually this gap is labeled overfitting, and we'll have to get deeper into what overfitting is. But in the first layer of approximation, you look up the manual, you see this, it's overfitting, solutions for overfitting, regularization. Okay, let's add regularization. There is one regularization function that I like very much, which when your neurons don't behave, it's called dropout, and it involves shooting the neurons to make them behave. Yeah, I like that. So let's see how this works. You have your neural network, and at each iteration of your training loop, you pick a probability. Let's say here p keep equals 75%. This means that there is a 75% chance for each neuron only to remain in the network. So at each iteration of the training loop, you roll the dice and you shoot 25% of your neurons. Boom, boom, boom. You remove them. And then on the next iteration of the network, of the training loop, you roll the dice again and shoot 25% of the neurons. And this is how you train. So the effect this will have is that during that one training loop, since this neuron is removed along with all its weights and biases and all that, those weights will not change on that iteration of the training loop. They will remain frozen. That's the effect. Of course, when you evaluate the performance of your neural network on test data, you don't do this on a brain-damaged network. You have to put all the neurons back. So the probability of keeping them will be 100%. That's how you configure to disable dropout when testing. I put for you the little code here in TensorFlow for dropout. Actually, it's just a one-liner. Dropout is applied after each layer. And what the dropout function does is very, very simple. It rolls the dice, and in the vector representing the output of the previous layer, it replaces 25% of the values by zeros. That's it. The remaining values, that's a small technicality, the remaining values are slightly boosted so as not to change the average of the whole vector. You need that, otherwise you would be shifting the activations of the next layer a little bit too much. But that's a little technicality. In first approximation, the dropout function takes the output of a layer, replaces 25% of the values by zeros, and that's how you continue. So, how does this work? Yes?
So in each layer of the network, let's say you have an input layer.
Yeah.
Let's say, so you're shooting the weights and biases, but you're still regarding the values of the inputs, correct? But just using weights, let's say, of 0, correct?
Yes, correct. Typically you would use a dropout layer after each, after the activation function. So Relu, that's the output of the activation function, then you add dropout. So obviously you wouldn't do this on the inputs. You first get through one layer of neurons, then you use dropout. And in the same way, on the last layer, the softmax layer, it will have a dropout layer before it, but not after it. So it's only between layers, then you add dropout.
But in a hidden layer, then, if you have a weight of 0, let's say, and so then you calculated in a particular neuron, if it dropped out, if you shot it, you're not even performing an activation for that neuron, right? And so
the activation for that neuron is 0.
The value is 0 coming into the next layer.
Yeah, right? Exactly. Yes?
For these neurons that are removed from the current iteration, backpropagation is performed or not?
So it is performed through 0, so it's not performed. Basically, the outputs of those neurons is a constant of 0, which no longer depends on their weights and biases, which means that their weights and biases are no longer present in the loss function computation, which means that the gradient will no longer have terms for those weights and biases, and they will not be updated on that iteration. So it's a way of, shooting the neuron. Mathematically, it's a way of freezing all the weights and biases belonging to one given neuron for one iteration. All right, let's see if this is useful. And actually, let us recap everything that we have done to our neural network. We started with a 5-layer neural network using sigmoids as the activation functions on the intermediate layers, and this is what we had. We replaced the sigmoids with Relus. Well, slightly faster to start, and actually we get a little bit higher in accuracy as well. Still very noisy, so we used a decaying learning rate that cleans up all the noise, and now we are sustained above 98% accuracy. But we have this overfitting problem, this disconnect between the test loss and the training loss. So let's start shooting our neurons. Let's add a dropout. This is what we get. So you see some noise comes back. That was to be expected. It's a brutal technique. You're shooting stuff. So yeah, noise comes back. The test loss function is largely brought under control. It's still disconnected by some amount from the training loss, but it's not shooting up anymore. So this, we're happy. It has the effect that we were hoping for. On the accuracy, well, first of all, I'm amazed that it didn't destroy our accuracy, given how brutal this technique is. But then I'm a little bit disappointed that it didn't improve our accuracy. Well, not in this case. You can't win every time. We'll have to actually revisit a little bit deeper what overfitting means. So, at its core, overfitting happens in a neural network when you have too many degrees of freedom, too many weights and biases. Imagine that you have so many weights and biases in your neural network that you can actually store all of the training examples in those weights and biases in some way. Imagine the network has so many degrees of freedom that it can create some kind of internal representation for each specific example of a one in your training data set. That would work for the training data, but it would fail miserably as soon as it was presented with a one that it didn't see before. So that's what overfitting is at its core. In a neural network, you need to put constraints. You need to constrain the degrees of freedom to force the neural network to create categories for your data, categories that then generalize to data that has never been seen before. The opposite side of this coin is, even if you have a small enough network, if you have very little data, you can still kind of store all of that data in the internal representation. So that's a constant takeaway for training neural networks. You always need lots and lots and lots and lots of data. And then, in our case, so yeah, 5 layers is a little bit, of overkill for this problem. But I tried to put 4 or 3 or 2 layers. I'm not getting above 98% accuracy even with that. I know I have plenty of data. 60,000 training digits for only 10 categories. That's fine. I even tried the textbook solution of adding a regularization function, and I confirmed on the curves that the regularization works. The test loss and training loss disconnect is largely fixed, but still I'm stuck at 98%. It doesn't seem to be possible to improve my accuracy. I'm hitting some kind of ceiling. So the last conclusion is that this network is by design, by some faulty design, not capable of extracting all the information that we need to extract from this neural network. Does anyone know why? We did something completely stupid at the beginning. We did. Did you spot it? Come on, who spotted the absolutely brutal stupidity we did? Well, you remember those images, 28 by 28 pixels? Exactly. We flattened them all in one line. We destroyed shape information. And come on, what are digits if not shapes? They're made of little circles and curves and straight lines and all that. We just junked all that. I'm amazed we are getting to 98% accuracy with that kind of approach. That's just not possible. But researchers have been working towards our rescue, and they invented convolutional networks specifically for 2D data where shape information, so locality information, is important. So let's see how convolutional networks work. Here I'm coming back to the example of a color image. Okay, so that's why I have 3 channels of information: red, green, blue. And now let's take a neuron. Again, this neuron will be doing a weighted sum of inputs. But this time, in a convolutional network, this neuron does a weighted sum of only a small patch of pixels right above it, a 4 by 4 pixel patch. And then the next neuron does again a weighted sum of this small patch of pixels right above him, but big difference using the same weights as before. We are reusing the same weights. So in effect, we have a little matrix of 4 by 4 by 3 weights here, and we are scanning the picture in both directions using that little patch of weights. So if we do this in both directions, and of course with proper padding on the sides, we obtain as many output values as we had pixels in the original image. And to do this, we used one weight per data item in the highlighted cube, so 4 by 4 by 3 weights. How many is that? 48. How many weights did we have before in the simplest possible 10 neuron network? Something like 8,000. Here 48. That's not going to work. Not enough degrees of freedom. So how do we add degrees of freedom here? Well, just do it again. Take another matrix of 48 weights and do it again. And that's what we do. We rescan the image using a different set of weights and obtain a second channel of outputs, again, one output value per pixel in the original image. And now, since we are using tensors, well, we can write those two tensors as one by adding a dimension with a value of 2, because we have two values, and this becomes the weights matrix for a convolutional layer in a neural network. So let's recap. 4 by 4. That is the size of the patches we're using. 3, that's how many input channels we have in our inputs. Here, a color image, 3 values per pixels, 3 input channels. 2, that is how many patches we pass on the image. And of course, that is also how many channels of outputs we obtain. So written in this form, with number of input channels, number of output channels, I think it's easy to see that you will now be able to stack those layers simply by aligning the number of outputs and the number of inputs of the next layer. We still have to solve another problem, which is to boil the information down. You see at the very end, somewhere at the bottom of our network, we still want to have only 10 neurons. Okay? So those, we need to boil the information down. One way of doing this, traditionally, was to sample those outputs. So it's important, I mean, it's useful to understand how this works because it gives you a good feeling for what those convolutional networks do. And actually, as those weights will be evolving during training, they will evolve towards small shape recognizers. There is a patch of weights that will evolve to react strongly to a little circle, another one that will react strongly to a little oblique line. And what you are saying when you are subsampling these outputs is, let's take groups of 2 by 2 output values, 2 by 2, so 4 output values, and in those 4 output values, I just take the maximum value and pass it down. I throw away all the rest. That's a way of saying, in this group of 4 output values, there is one that is big, which means that this one corresponds to something that has been seen clearly above, like a little shape, and the 3 others correspond to, I've seen nothing. So you can throw them away. That's how traditionally we've been boiling the information down, but actually there is a simpler way. I'm not claiming it's more efficient, it's just simpler. When you pass the patch on the image, instead of doing it pixel by pixel, you can also do it every 2 pixels. And if you do it every 2 pixels, well, mechanically, in the output, instead of obtaining 1 value per pixel, you obtain 1 value per group of 4 pixels. So that's another way of boiling the information down. And actually, you will see in most recent convolutional networks, you see only convolutional layers. And people play with the stride to boil information down. So this is the neural network that I want to build with you. On the top, our image. First layer, first convolutional layer. let's look at the shape of the matrix. So 5 by 5, that's the size of my patches. I'm using patches of 5 by 5. Reading in one input channel because I have a grayscale image. It has only one channel of information. The last number is 4, so I'm using 4 of those patches, producing 4 channels of outputs. Next convolutional layers. This time I'm using smaller patches of 4 by 4, reading in 4 channels of information because I output 4 channels of information previously. And this time I apply 8 of those patches, resulting in 8 channels of information. This time with a stride of 2. So now my planes of output values, they are not of size 28 by 28 anymore. Now they are of size 14 by 14. Third convolutional layer, again, patches of 4 by 4, reading in 8 channels because I was outputting 8 channels before, and I apply 12 of those patches, producing 12 channels of information. Again, a stride of 2, so those information planes are 7 by 7 now, instead of 14 by 14. Then I apply a fully connected layer. So a fully connected layer is a layer as we have seen up to now in this session. In a fully connected layer, each neuron does a weighted sum of, this time not a little patch, but all the values in the 7 by 7 by 12 cube of data. All the values. And the next neuron does again a weighted sum of all the values using its own weights. Different weights per neuron. So that's a fully connected layer. And then, lastly, our layer with just 10 softmax neurons to produce our final categories. So, let's see how to write this in TensorFlow. So again, you need a weights matrix and a bias vector per layer. The only difference is that the convolutional layers have a weights matrix with a specific shape, which we have seen before. So size of the patch, number of input channels, number of output channels. For the fully connected layers, the shape of the weights matrix is as we have seen before, number of inputs, number of neurons. And this is what our model becomes. So TensorFlow has this quite useful conv2d function, which doesn't do anything fancy, it's just a double loop. You give it an image, you give it a weights matrix, and it will apply those weights in a double loop on the image, producing this plane of outputs. Don't mind the complicated syntax for strides, okay? I put in red the numbers that need to be either 1 or 2 to get a stride of 1 or 2. You can read the documentation to understand the rest. And the padding strategy, so we have images on a white background, so adding more white background is a good padding strategy. That's what we have here, padding is the same as the borders of the image. So conv2d produces those 28 by 28 planes of values. We add the bias, and we feed this through the Relu activation function. Next layer, the same thing, but we use the output of the previous layer as our input, and so on. Then as we want to go into the fully connected layer, we need to reshape this, this little cube of 7 by 7 by 12 values. We need to reshape it as one vector so that we can input it into a fully connected layer. That's what we do. And then our 2 fully connected layers, one with a Relu, one with a softmax. I hope by now you're used to those one-liners representing one fully connected layer in a neural network. So, let's see how this works. And actually, well, I can show you the real demo, but then we will look at the video because it's slightly slow. Sorry, not this one, this one, this one, this one, this one. Run, run, run. Okay, so obviously we are asking this system to do a lot more, so it's slightly slower than it was before. But still, you see the accuracy shooting up quite sharply. You see we are not even at 200 iterations, we are already at 96% accuracy, and it's still shooting up very, very sharply. Let's play the video to see how this ends. So we'll have to zoom to see something. You see the 99% line there. We're getting there, we're getting there, we're getting there, we're getting there, and we are not getting there in the end. 98.9% accuracy. Oh, damn. I really wanted to get to 99 with you here today. So, what else can we do? Actually, if you look at the curves, still have this, problem. You remember this one? You remember what the solution is for this one? Dropout, exactly. And actually, what I'm going to give you is a trick, but let's call it a methodology for coming out with an ideal neural network for a given problem. What you do is that you restrain your neural network a little bit too much, okay, until it hurts. Here I know I can get higher than that. But I did not give it enough degrees of freedom to fully go there. Actually, you can see that on the parameters I used. In the first layer, I used 4 different patches, which means that I will be recognizing 4 different basic shapes. Well, I think that's a bit limiting. All the numbers are not really made of 4 basic shapes. So once I know I'm hurting it a little bit, I give it more degrees of freedom, and I add dropout to make sure that those additional degrees of freedom are not going to result in overfitting. So that's what we do. Slightly bigger patches, but most importantly, instead of using 4, 8, and 12 of the patches on each layer, now I'm using 6, 12, and 24 of them. More degrees of freedom, and I add dropout on the fully connected layer. I'm a little bit hesitant about shooting neurons in the convolutional layers because you have seen it previously. We have significantly less degrees of freedom in these convolutional layers. So I'm a lot happier about shooting neurons in the fully connected layers where I have plenty of neurons to shoot. So let's see how this performs. So you see the accuracy shooting up very fast. I will have to zoom to see what is going on. Let's zoom, zoom, zoom. Look what the 99% line is, and we're above. Yes! Thank you. Actually, using this approach, you get to 99.3% accuracy, which is not so bad, considering that, 100% is not so far away. If you go to the MNIST website, you will see that the current world record is 99.7. So here together in an hour, we got within a couple of 0.1% of what is the state of the art on this problem. All right, I want to visualize here what dropout did to us. So this is the bigger network, already with more degrees of freedom, and learning rate decay and everything done by the book, but without dropout. You see it is already above 99% accuracy, but still exhibits this bad overfitting problem. Now I add a dropout on the fully connected layer, and boom. The test loss is brought back under control, and this time, yes, I won 0.2% of accuracy just with dropout. I went from 99.1 to 99.3%, which is huge. I mean, we're fighting for the last percent here. It has only 0.1%. So in that last percent, actually getting 0.2% just with a little regularization technique, that's huge, that's fantastic. I love it. All right. So, that is MNIST. I have a last trick to show you on MNIST. actually a last superpower. But let's check the time. 9:30. Isn't this the time for the break?
Yeah.
I think it is. It's the perfect time for the break. So I will be welcoming you here in half an hour sharp to talk about the last superpower, which you don't know anything about yet, so please come back. And right after that, we'll dive into convolutional neural networks, which are a lot of fun as well. Thank you. Welcome back. Okay, I'm glad I didn't scare too many people, so we still have most of the audience with us here. All right, let's kick this MNIST dataset out, because I'm a bit fed up with it. But I still want to show you one last trick. We have seen dropout, but there is a better regularization function that has appeared recently. And if you do any work in neural networks, it's something you can't ignore, and it's called batch normalization, and it's super powerful. So let's see how it works. But before, let's imagine we have this kind of data to work with. Hypothetical example, we have two values that evolve like this, and we are tasked with predicting something out of this. So first of all, you see this is very bad data. The A value is between 0 and 20. The B value is between 0 and 2. So they are not on the same scale. This will be problematic in a neural network, because when you put data in, it's reading the data in, multiplying it by weights, but those weights are basically fixed. So something that is in the hundreds will produce much bigger activations than something that is on the order of magnitude of 1. And the neural network will have to adapt its weights to compensate and work to do that. So we can clean this data a little bit. Let's rescale it, reshift it to be well centered around 0. And as we do that, oh well, damn, now we realize our data is correlated. Those two curves seem to represent, roughly the same thing. They evolve in tandem. You see it on the scatter plot here, that there is a 45-degree line that seems to be a strong correlation. So, okay, when you are a data scientist, you see this. You still see signal in the differences between those lines, so let's decorrelate. Let's use one signal, which is the average, and the other signal, which is the difference between those two. And now, lo and behold, I have two data sets that seem to be different enough, not telling me the same thing, so they might be useful inputs for a neural network. And on the scatter plot, you see that now they are centered, well scaled, and the correlation along the x-axis along the 45-degree axis is gone. What we just did is called principal component analysis, and it was done by hand here, but basically what it is a matrix multiply with a matrix add. We had our data, we multiplied it by a matrix that scales and rotates the data, and added a shift to recenter the data around 0. So this is useful and for neural networks. And if you read traditional neural network literature, you will always see this kind of advice. Please whiten your data. What they call data whitening is exactly applying principal component analysis, well, basically rescaling and decorrelating your data before you use it in a neural network. But look, it's just a matrix multiply. Doesn't that matrix look like a weights matrix, and the other matrix looks like a bias metric? Couldn't a neural network do this? Just add an additional layer and let it learn those parameters. Why do I have to look at the data and figure out which are the correlation axes and all that? That's just a neural network layer. Let's add a layer and let it figure it out. So actually today, that's mostly what we do. you will see less and less people actually whitening their data, because CPU is relatively cheap, adding an additional layer is relatively cheap, and you can work with slightly dirty data, and especially you can let the network determine what the right cleaning of the data is. But what happens at the output of the second layer? Is the output of the first layer clean? I mean, again, decorrelated, centered, and so on, to be input into the second layer? Well, maybe it's not. Oh, okay, but I know, I just added another layer that cleans it up. Yeah, that could work, but in the end, it means you will be doubling all your layers. That is starting to be expensive. There must be a better way. And that way is called batch normalization. And this is exactly what batch normalization does. Between each layer, it re-normalizes the activations, but in a smart way, to make sure that the inputs of the next layer are properly centered, scaled, and so on. So how does it work? Oh, first of all, yes, you can see this on the curves. If I go back to my 5-layer network, okay, that we had previously, and on my percentile histograms here, I display what is usually called a logits. That's just the raw weighted sums plus bias. So that is the input into the activation functions. All the activation functions of all the neurons in the 5-layer network. Well, you see what goes into my activation functions is kind of a Gaussian, but it's very flat on the sides. I see most of the values in the middle, and if you look very carefully, actually they are not in the middle. The 0 line is above where most of the values are. So my values are actually distributed like this. It's a bell curve. It does look like a bell curve, but it's not centered on 0. And I put you in the background the sigmoid, which is the function I'm using as an activation function. So you see, with a distribution of values like this as inputs, well, my outputs will mostly be in the small regions of the sigmoid. And actually, if I look at the activations, that's what I see. I see a very skewed distribution. I have 1 percentile, the intermediate color of green here, which is taking up all the space on the graph, and I have just little bands on the sides. So I am, after the activation function, I do have a distribution of values that is very, very, very skewed. What can I do about this? Well, batch normalization has 3 big ideas. We work on batches. So we have 100 images and labels in each batch. On those batches, it is possible to compute statistics. So let's compute the statistics for the logits, so the weighted sums plus bias, at the output of a neural network layer. Those weighted sums plus bias, we can compute statistics over the mini-batch on it. We can compute what its average is, we can compute what its standard deviation is. Then we can use those to rescale those logits. Again, logits, that's a specialized word, but it just means the raw weighted sums plus bias before the activation function. So now on this mini-batch, we are at the output of, we are looking at 1 layer. We have not applied the activation function yet. We have just the raw weighted sums and plus bias. We compute our statistics on this, and we can rescale and recenter those values by subtracting the average and dividing by the standard deviation. That's what we do, minus average divided by standard deviation. The plus epsilon is for numerical stability to avoid doing divisions by 0. Okay, we forgot one thing. I also told you that it's good to decorrelate the data. Well, that would be too complicated here, too costly. So we don't do that. Just rescale and recenter. But now, didn't we destroy information? Well, maybe the fact that a neural network layer is actually outputting values that are skewed to one side, maybe that's significant. Maybe that has some value in the neural network. Maybe recentering this is destroying information. Maybe that's not good. So we need to do something to preserve the full expressiveness of our model as at the same time that we do our statistical modifications to make the model work better. And the genius idea in batch normalization is once you have rescaled your logits, you scale them back using two learnable parameters, alpha and beta. As previously you had biases in each neuron, you simply add two additional degrees of freedom per neuron, just two per neuron, called alpha and beta, a scalar and an offset factor, and your batch normalized logits become the scaled and recentered logits multiplied by alpha and plus beta. Now, why does this work? Well, just to prove it, look, there are values of alpha and beta that will give you your original x back, if that was the right thing to do. If that was the right thing to do, the neural network during training can decide to assign to alpha the standard deviation value and to beta the average value, which basically means that the batch normalized logits are the initial logits, and you haven't changed anything. Just a second. So that is just to prove that with some values of alpha and beta, we are back to our original network, and that proves that we have not destroyed any of the expressiveness of the network. There are values for which it does exactly the same thing as before, if that is the right thing to do. But those two values, we let the system learn them. So if there are better things to do, it will learn that. Yes?
Is there one instance of alpha and beta
Per neuron.
per neuron?
They play the same role as biases before. There was one bias per neuron. Now here is one alpha, one beta per neuron.
And we're centering and rescaling weights and biases as opposed to inputs?
No, we are centering and rescaling logits, which is very precisely in each layer the weighted sums plus biases before the activation function. So we are centering and rescaling before the activation function precisely so as to pump into the activation function values that take maximum advantage of the useful portion of the activation function.
So we're not centering and rescaling the inputs.
Well, in a way we are, because the first layer is a linear combination of the inputs, and we are centering and rescaling that. So yes, in a way we are. But yes, we are officially skipping the data whitening part because, as I said, one layer of a neural network can do it, and here one batch norm layer can do it even better. All right. So now the last thing to prove is didn't we actually break something in the gradient computation? Are we still capable of computing gradients using this as our logits instead of the non-batch norm version? So let's look at it. X is the weighted sums of inputs and biases. That obviously depends on our weights, biases, and images. The average of X on my mini-batch, on my one mini-batch, well, on that one mini-batch, all the images have been processed with the same biases and the same weights. So that part also depends on my current weights and biases. That's fine. Same for the standard deviation. It's computed on the current mini-batch. So it uses the current set of weights and biases. So that's what I want you to prove. X depends on the current weights, biases, and images. The transformed X, and of course also the alpha X plus beta, those are just constants, they also depend on the current weights and biases. So yes, it is perfectly possible to compute a gradient of batch norm dx of x instead of the gradient of x that we were computing before. There is no difference, and the batch normalization can be added as simply a layer between your weighted sums and your activation function, and the back propagation, the gradient computation will still work normally. That's the beauty about it. Okay, so let's see it in action. You remember? 5-layer network with sigmoids as the activation functions. And we had this as our activations because the distributions, the inputs of the activation function was skewed. Let's add batch normalization and train again. This is what we get. Look, our activations. It's a perfectly beautiful Gaussian now. All those bands are evenly distributed across the full useful range of our activation function. And here I represented it. So the Gaussian of inputs is centered on the linear part of the activation function. So actually, with batch normalization, we can even train deep neural networks still using the sigmoid as the activation function, if that was the right thing to do. Does it work with Relus? Well, actually it does. You see, this is what I get with Relus. Different things on the graphs. Remember here, don't remember, but here I switched to my convolutional network we had previously, which had 3 convolutional layers and 2 fully connected layers. So here I'm actually displaying the activations, so after the Relu function, on the convolutional layers and on the fully connected layers. Also, just a technicality, but since this is a Relu and the Relu is 0 in all the negative side, on a mini batch, a lot of values will be 0. I don't want those in my graph because that's not part of the distribution that I want to display. So what I'm displaying here is the maximum activation on one mini batch, the maximum value taken by one neuron output on one given mini batch. And what I get is, again, a beautiful distribution across the useful portion of my Relu. Instead of being completely skewed on one side, you see these percentiles here. You can kind of see that it's a nice bell curve that is centered around, for the dense layers, around 2.5, so squarely in the positive range of the Relu, where the Relu is useful, it's a linear function. And for the convolutional activations, actually it's centered around 1.5, a little bit of skew in the Gaussian, but not by much. So it works beautifully both on with sigmoids, and it's still useful with Relus. Just a couple of technicalities. This is something you will forget as soon as I switch off this slide. That's what I do. But still, the batch norm layer comes between the weighted sums plus bias and the activation itself. Remember, the batch norm layer removes the average on the batch, so our biases are actually not useful at all anymore. Having plus bias and removing the average, it means that the bias is gone. So when you use batch norm, no more biases. The beta factor in the batch norm actually plays the role of biases in batch norm. Also, when you use a Relu, well, a Relu is 2 linear segments. So if you modify the scale of your inputs, the scale of your outputs will be modified proportionally, which we don't care about. It doesn't change the shape of the output distribution. If you use the sigmoid function, of course, if you scale your inputs, you will be getting into different regions of the sigmoid, and the shape of the distribution will be completely changed. So when you use a sigmoid, it is important to learn also a scale parameter that rescales your values in the useful portion of the sigmoid. With Relus, you don't care about that. So if you use Relus, you can skip the alpha factor and not use it at all. So here I give you in a little chart with and without batch norm, if you're using Relu or sigmoids, which of those biases, batch norm scales, batch norm offsets you are to use. If you use TensorFlow, you actually have to specify those parameters and say which ones you want, which ones you don't. So it's useful to have this little reminder. So what is the end result? The end result that the activations being cleaner, you can go a lot faster. And that actually for me is even a little bit of a problem, because it means that now you have to you can get much better results, but you actually have to change your learning rate to get them. You need to use a faster learning rate. That's a good thing, of course, but it also means that when you apply batch norm, you have to go back and the learning rate that you had previously doesn't work so well anymore, and you have to find a new learning rate that works better. Also, this does the same kind of regularization effect as dropout. So it's possible to completely stop using dropout and use batch normalization instead. It's also possible to combine them, but use a lower amount of dropout. And that's what I did here in this last network. Oh, last little technicality. How do you apply batch norm on a convolutional layer? So you have to compute those, statistics on the output of one, so the logits of one neuron across all the possible values in a batch. But when you do convolutional layers, one neuron, has a given output per image in the batch, but you're also scanning the images using the same weights. So it's per image in the batch, and per X position in the scanning, and per Y position in the scanning. So that's the only little change. The averages and standard deviations, which you were computing previously on the whole batch, in a convolutional layer, you need to compute those statistics on all the images in the batch and all the positions in X and Y of your neurons. So it's just the computation of the stats that is different. But you still have one scale factor and one offset factor per neuron, just as you had one bias factor per neuron previously. Okay, and last thing, now at test time, when you're actually testing on real images. So batch normalization uses those statistics. What do you compute those statistics on at test time? Do you use the last batch? Why is that relevant for your test images? No, not really. Do you use all the images you have? Well, that would be good statistics, but that's a bit expensive, So actually the practical trick is during training to use a shifting average and a shifting standard deviation, which means that you are using the stats you computed on your last something iterations, and that's what you use as the batch norm factors when you do testing. Basically, the assumption you're making is that across those last iterations, the weights and biases will not have changed that much, so your statistics are still, quite good for this. Okay, so the code. TensorFlow has a very useful batch normalization function, and right here at the bottom, batch normalization. But if you look at the code, it actually does nothing. You give it logits, but you have to give it also the averages and the standard deviations. And yes, very helpfully, it will do the minus and do the division. Thank you. I would have known how to do that myself. All the rest of the complexity, how to compute the averages and the standard deviations correctly in dense layers, in convolutional layers, you have to do yourself. And how to compute your moving averages so as to use them when testing, you have to do yourself. It's not that complicated. TensorFlow also has this moments function, which returns the average and the standard deviation. So that's perfect. You can use it. And you see the only change between a convolutional layer and a non-convolutional layer is that I test and I use moments computed on a different data set in both. That's the only difference. And TensorFlow also has this exponential moving average function, which you can use to compute your moving averages, so that here my M and V, which are mean and variance, I put in a condition, conditionally on being in training mode or test mode. I'm using either the statistics computed on the last batch or the moving average computed on a number of batches before. For testing, that's what I need. For training, I just need the statistics on the current batch. So, barring those two little complications, that for convolutional and normal layers, the stats are slightly different, and that in testing and non-testing environments, the stats are a little different. The core of it is just batch norm, the logits, the average and the variance, and then the offsets and scales. That's my alpha and beta factors, which I need to define as variables because they will be learned. And this gives me a layer which I now apply between my weighted sums plus bias if I use one, and my activation function wherever I want batch normalization. Does it work? Well, let's try. This is my convolutional network, which I had previously. Remember, I got to 99.3% accuracy with my best neural network. Now applying batch normalization, you see 99.3, it's kind of far away already. This is shooting above 99.5. So with batch norm, I'm still keeping a little bit of dropout, but with batch norm here, in my fight to get the last 0.1%, I got 2 additional 0.1% again, just with another normalization technique, regularization technique. I love batch norm. All right, so let's close on this superpower. And now let us change worlds, and we will be diving into recurrent neural networks. Just a very quick mention about TensorFlow. TensorFlow has this tf.learn library, which today you will find in tf.contrib.learn. It moves into the main distribution as of TensorFlow 1.0, which will be released soon. I'm just mentioning this in passing because everything we have seen today was low-level TensorFlow. We have been manipulating matrices. But actually, once you understand what you're doing, once you understand which layers you want and so on, you want to manipulate layers individually. So there is an API, I'll skip over this quickly, but there is an API in TensorFlow to manipulate layers directly. And to give you a little feel from it, this is how I could write my convolutional model. So you see, it's layers, convolutional layer, layers, convolutional, then a layer flatten, layers Relu, that's a fully connected layer, layers linear, that is a fully connected layer but without the activation function, and so on. And actually, in tf.learn, the contract is that your model function returns a dictionary of whatever you want. Okay, so it's very flexible. I'm very fond of this API. You return a dictionary of whatever you want, depends on your problem, plus the loss and the training operation. Okay, and then what you can do with this is create an estimator. In the estimator, you pass your model as the model fn function. And instead of writing yourself a training loop, you just do estimator.fit. Pass in the images, and that runs for whatever number of iterations you specified. So it's the same as we have seen before, just written with less code. And you see the added value is that all those layers are creating themselves their weights and biases and all the other degrees of freedom that they need. I don't like to start with this because there is a lot of hidden stuff going in the background, and if you don't know what that is, it doesn't help with understanding. But once you understand, this is obviously a much more user-friendly way of working. There are ways of seeing the learning statistics as well. Actually, the way that works is that in the fit, by default, it will give you the learning statistics, but just the loss, because it knows what the loss is. If you need more learning statistics, you define a metric. In this metric, maybe I have the code here. Where is it? Oh yeah, I have it here. See, eval metric. You actually say on which key here my model is outputting a dictionary of whatever I want. So if I want to compute a metric on one of those values, I define a metric using the metric spec function where I say on which key I'm computing this metric. I specify the function computing this metric, and now I can use this eval metric into a new object which is called a monitor. And this monitor, you can pass it as a parameter to the fit function. That's how you do it. So you create a monitor. The monitor, you say, please follow this metric. The metric being whatever you want. It's just a function plus a key in what you return. So it's you who define it. And then this monitor, you configure it saying how frequently you want to check that value, and it outputs that. All right, so recurrent neural networks. Who has worked with recurrent neural networks already? Yeah? Less people. Okay, we'll go slow. So this is a neural network as we have seen previously, a couple of layers. But now the trick in recurrent neural networks is that the activations of these intermediate layers at each step, we will actually re-inject them as part of our inputs. And a recurrent neural network will be used in time steps. At one time step, I take one input. Maybe the internal state will be 0 at that point, and I compute one iteration of this network. I go through this neural network once. That creates activations in this intermediate layer. Those activations, I concatenate them to a new input vector, and I repeat. So basically, you can represent this as a neural network cell. It has inputs xt, which will be changing with time. Those are vectors representing something. It has this h internal state, which at each step is computed, and at the next step re-injected into the inputs. And this h state is also used to compute the outputs via a softmax activation layer. So an additional layer, which is usually represented outside of the cell. Okay, that's the usual representation, those yellow circles, and which takes the h internal state, applies a softmax layer to it, and computes something that is useful to us. Again, a vector. So these are the transfer functions for the most simple, the simplest possible cell of a recurrent neural network. You see the inputs, you calculate them by taking the real inputs and concatenating the previous internal state to it. You just concatenate. It's a vector of n elements and another vector of p elements. You concatenate them into one big vector of n plus p elements. Then you feed this through a normal neural network layer. Here, the usual activation function to use is the hyperbolic tangent, which is just a sigmoid shifted, scaled by a factor. It's a continuous function going from -1 to 1, instead from 0 to 1 as the sigmoid was. And then those intermediate states, that is what you will be re-injecting into the next step. If you want to compute outputs at this point, you add a new neural network layer, this time with the softmax activation function, to compute your outputs. All right, so this is nice. This is like a state machine. So this will be very useful for sequences. And since it has internal state, it will be able to do all the things that state machines do, like remember that something happened at one point in the sequence, and do something else at another point in the sequence based on that. For example, you will be able to train this on a sequence of characters and teach it to correctly open and close parentheses. That's one thing that this can represent as a state machine. But the problem is, how do you teach it? Well, on this cell, let's imagine we put something as the inputs, and it produces some outputs. Okay. Now, we know what our desired outputs are. So we force those desired outputs and try to do a retropropagation to change our internal weights and biases to produce better outputs. Well, okay, that's going to work if the problem were the weights and biases. But what if the problem was the input state? Here represented as 0, but obviously if I'm not starting, if I'm somewhere in the middle of my sequence, oh, thank you. I will update my software later. Thank you very much. What if I'm in the middle of my sequence and my input state is ht minus 1, and what if it is that state that is not correct? Well, my retropropagation step can fix my weights and biases, but as far as this transfer function goes, the input state is a constant. I can't change it. There is no amount of learning that can force those values to something different. It was received from the outside, it's a constant. So even though those things are capable of representing state machines and state changes, I don't seem to be able to teach them to meaningful state changes. The solution is to unroll this cell multiple times and to consider the whole of this as one training step. Well, now, if my last output, y5, is not what I want, I can force my desired output here, do a retropropagation step, and if the problem was that h3 or h2 or h1 or h0 did not have the correct values for this to work correctly, well, now I'm retropropagating through all of that, so I will be able to change the weights in such a way as to influence h0 and in such a way as to influence h1, so that h4 going into my last cell actually has the correct values and produces the desired output. So that is how training works for recurrent neural networks. You have to unroll the neural network across a certain number of time steps. And then you put in your inputs, you put in, it produces some outputs, you put in your desired outputs, you do one training step computing weights and biases, and you modify those weights and biases to get closer to your desired outputs. But this time, since it is unrolled, there are ways in which you can influence the values of h4, h3, h2, h1, and so on, if those were the culprits, simply by modifying the weights before you calculate them. And please remember, it's the same cell. So when I say the weights and the biases, I'm talking about the same weights and the same biases in each cell, and also in the softmax activation layers. It's the same weights and the same biases. But that doesn't matter. This is just a transfer function where there is a loss calculated from the inputs, the desired outputs, and which uses as parameters the weights and biases in the system. From this loss, I can calculate a gradient, which means that I can now change my weights and biases meaningfully. It doesn't matter that it's the same weights and biases in each cell, because this is one cell replicated multiple times. I can also stack them. Well, if I need, deep learning, I want to go deep. So if I want a recurrent neural network that is not one layer, but 2 or 3 or 4 layers deep, that's what I do. It doesn't change anything. I still have an input, I still have an output, and my state vector is now slightly more complex, but whatever, it's just a state vector. So conceptually, this doesn't change anything. A stacked cell is just a cell in a recurrent neural network. To teach it, the same thing, you replicate it multiple times. So, is this going to be capable to represent state changes across, large portions of text? Imagine here, we are using this recurrent neural network to predict the next word in a sentence. So we feed in all the words, all the initial words in the sentence, and we're trying to predict the next. I skip over how do you encode words into vectors. We'll talk about that later. For instance, for the time being, just imagine that we have a solution for that. So, if my sentence is, his mother tongue is something, well, that is a short sentence, so even by unrolling my network 5 times, I can teach it that if the beginning is his mother tongue is, what comes next is most likely a language name. That works. But here, the context saying that this guy was born in France is far, far, far away, somewhere up there at the beginning. How can I teach it that here it has to output his mother tongue is French and not just any language? Again, the only way you can teach it that is by unrolling this sequence as many times as there are words in this full sequence. It's the only way. So the conclusion here being that recurrent neural networks will be able to be taught state changes across spans as big as the number of times you unroll them, and no bigger. That's a fundamental limitation. It doesn't mean that they cannot represent state changes across bigger, if you work with a character level recurrent neural network, for instance, and you teach it to open and close parentheses, you can very well teach it to open and close parentheses on, let's say, 20 character sequences, and it will still work on 50 character sequences, because internally it has what it takes to represent the fact that it has 2 open parentheses, does things, and at one point it decides to close those parentheses, even if that point is beyond the 20 character limit. So it can represent these state changes, but you can't, if it gets it wrong across a span of more than the unroll time, then there is nothing you can do to train it to get it right. So the conclusion here is that recurrent neural networks, to be useful, are always deep, always very deep. You see, previously my non-deep networks had 5 layers, and I told you that, in the worst cases, people who were here on big stacks for recognizing images, we get to 100 layers. That's like, whoa, super big. Here, the simplest thing I just threw on the board, already I see that maybe 30 or 40 is my unroll size, just to start with. So these guys are always very deep. And you get into all the problems of deep neural networks, vanishing gradients and all of that. So for a long time, these guys did not work. Until we found a cell architecture. So here the solution was to work on the cell architecture to make sure it had good convergence properties. So I'm not going to enter into the math why the convergence properties are better, but I want to show you the solution and how it works. And the solution is called an LSTM. And now I do a survey. Do you prefer the super complicated, incomprehensible diagram, or do you prefer the super complicated, incomprehensible set of equations? Which is your favorite way of explaining things? Diagram. Okay, well, I'm a developer. I prefer code. And this thing looks like code, so I'll actually skip this is the usual diagram you see in textbooks. It doesn't make sense to me, I'm sorry. So, yeah, let's put it on the side, and let's simply walk through the code, which are the equations defining what this does. It's actually not that complicated once you realize that we will use a couple of networks layers to define what is called gates. So, of course, our input is again the concatenation of our real input plus the internal state. And now we use a first network layer. Here the sigma is for a sigmoid, which computes an internal vector of values between 0 and 1. That's why we use the sigmoid, because it's values between 0 and 1. Why do we call it a gate? We call it a gate because these values being between 0 and 1, we will be able to multiply another vector element-wise by this one and gate the values in that vector. So if it is zeros, those values will be gone. If it is ones, they will go through, and we have all the intermediate states. So we define one forget gate, one update gate, and one result gate with different weights. Now, our input, so now the idea is that we will be maintaining a second internal state here called C, which is a kind of memory. And what we want to express here is that at each step, the new contents of my memory will be the previous contents minus what I choose to forget, plus what I choose to remember from my inputs, from my new inputs. That's conceptually what we want to write here in equations. First of all, a technicality, I put on the side the sizes of all these vectors. And it's actually quite simple. All the vectors inside of the cell are the same size. Here I call n. That's by design. So that's one hyperparameter of a recurrent neural network that you have to remember. It's the internal size. Now, I have just a problem. My inputs are of size p plus n, because I concatenated my internal state, internal, so size n, like everything else, and my true inputs. So I can't use it as it is. Well, okay, let's use a neural network layer to bring it down in size. That's what I do through this hyperbolic tangent neural network layer. By the way, this line is the equivalent of what I previously had in my simplest possible recurrent cell, as my hyperbolic tangent line. And this line is also where you can play with the activation function. If you don't like the hyperbolic tangent, you can use the Relu function here. That works as well. Here, you can use the the Relu or something else. The sigmoids, you can't use anything else but the sigmoid, because the goal is to obtain values between 0 and 1 and use them as gates. So you have to use a function that is between 0 and 1. So now that I have size adapted my inputs, I can compute my new internal memory state C, which is forget gate multiplied by its previous state. So it's what I had previously in memory, multiplied by what I want to forget, plus update gate multiplied by my inputs, so plus what I choose to remember from my inputs. That is my new internal state. And the, let's call it external state, H, LSTMs have two states. This state is basically the result gate multiplied by my internal memory state C. The hyperbolic tangent here is just a size adaptation. That's all it is. That's not a network layer. If you look at it, C can grow. Okay, all the parameters are between 0 and 1, but C is the sum of two such parameters. So at one point it can be 2, and the next step it can be 3 and 4. It can grow. So we use the hyperbolic tangent to bring it back between -1 and 1 when we use it. That's a technicality. My output state is the result gate, so whatever I choose to show to the outside as a part of my inside memory. And of course, if I need a comprehensible output, I add my softmax layer at this point. So these are the equations of an LSTM. The general principle is still the same. I have an input, I have an output, I have an internal state that is passed around. But the rules for updating the internal state are slightly more complicated. And actually, these are not the only rules possible. You can imagine those arrows going into plenty of different ways. And there was so much variation that one guy decided to test all of them. He wrote a big program to test all the possible variations. And he came to the conclusion that most of them were performing just great. So today, I like this guy with ideas. He always talks sense. Today, the most popular of those recurrent network cells is called the GRU, gated recurrent unit. So very similar equations. The only difference is that it's just as powerful as an LSTM with only 2 gates instead of 3, so that's 1 less weights matrix, 1 less bias vector, cheaper to compute. And apart from that, well, slightly different mechanics inside, but externally, it's just a cheaper recurrent neural network cell. So that's what we will use. Let's use it. We will do something fun. We will teach a neural network a character-based language model. We will give it text and ask it to predict the next character in the sequence of text. So that's how it works. We have those cells. We unroll it a certain number of times, and we put on the inputs characters. How do we encode these characters? We need them as vectors. Well, one-hot encoding. Okay, we had that before. So here it's an alphabet, let's say roughly 100 characters. If I take lowercase, uppercase, plus a bit of punctuation, that's about 100 characters. So we are working with 100 element vectors, and the way to encode an S is to use a vector of 100 zeros with a 1 somewhere in the middle, and the index of this 1 is the numerical value for S. So we put our text on the inputs. And what we force, so it will produce some kind of text on the output. To teach it, we force a sequence on the output, which is the same text shifted by 1 character. So it's the same characters until the last one, and the last one is new. And this is what we will be teaching. So let's write this in TensorFlow. So first of all, there is a full API for working with recurrent neural networks in TensorFlow. It starts with a cell. So let's use a GRU cell. I like the GRU cell. And by the way, when you say GRU cell, okay, this defines all the weights and biases that we had internally here. You see there are 3 weights matrices, 3 bias vectors. All that is defined internally when you say GRU cell. The only parameter you need to specify is this internal size of the vectors in this cell. Remember again, internally, all the internal vectors are of a size n, which is not the same as the input size, which is not the same as the output size. You have a softmax layer on the output, so you can adapt the output size to be anything you want. The input size, the internal size is a free form, is a free parameter. Okay, now I want a deep neural network, 3 deep. Let's stack it. There is a function for that. It's called multi-RNN cell. You pass it a cell, you say how many times you want this cell, and it creates a new cell for you, which is a stacked cell. And now the last thing we need to do is to unroll it. Again, in TensorFlow, you do this using the dynamic RNN command. you give it the stacked cell that you just produced. How many times do you unroll? Well, that will depend on the shape of X. Okay? X here, my inputs, is a sequence of characters. So if I feed it with sequences of 5 characters, my network will be unrolled 5 times. And what is fantastic in this API is that dynamic RNN actually doesn't, you remember this is all TensorFlow code, so this TensorFlow code doesn't actually, so produces a graph in memory, and here dynamic RNN doesn't actually physically duplicate this piece of the graph in memory. It uses a graph node, which is a for loop. It exists. TensorFlow has that, and they managed to get the gradient computation and backpropagation to work somehow across those for loop nodes. I don't know how that works, but it's magic. But it means that this actually adds a for loop as a node in your computation graph, which means that at training time, it will be able to unroll this 5 or 6 or 7 or 3 times. It's very flexible. In our case, it's not very useful because all of our input sequences will be the same. We take chunks of, what did I choose? Sequence length 30. We take chunks of 30 characters of our text, and that's what we train on. But if you are working with sequences which can have different length, well, there's nothing to do. You just pass the length of the sequence, and dynamic RNN will unroll your RNN cell as many times or as needed on a per example basis. Okay, and I need to pass in my initial state, because of course I'm passing the state around. So, what I get as an output is results. So it's all the ages on the bottom. I will need to apply a softmax activation layer on those to obtain my result characters. And I get also the last state, age, which is the state that I will need to pass back in the beginning as I continue my training. All right. How do I write this softmax activation layer? Well, I know how to write a softmax activation layer, but I have one problem to solve. All the weights of these cells are shared. So as I compute my softmax activation layer, a softmax activation layer has a weight matrix and a bias vector. I want also to share the weight matrix and the bias vector below each cell. There is a technical solution in TensorFlow. When you define a variable, you can either say variable, which gets you a new one, or you can say get variable, which gets you one that exists by name. So this would be a very simple way of defining here 8 softmax cells using the same weights and the same biases. But actually, you can do something even simpler here. Look at the output state that we have, H0, H8. Let's call it HF. Its initial size is batch size. Well, yeah, we will still be processing batches. So that's a slight complication. Every size here will start with batch size. Let's ignore that. It's sequence length and cell size. Because how many of them do we have? Well, as many as we unrolled the sequence. And how big is each vector? So those are state vectors, so their size is the internal size of the cell. But now, as we process them through our softmax activation layer, we're actually processing one of those H's because it comes from one of the iterations of the cell, or because it comes from one of the batch examples. That's the same. So let's just treat those H outputs exactly the same, whether they are different because they come from a different example in the batch, or because they come from a different iteration of the cell. So the only thing we do is that we reshape this vector into a big bag of vectors batch size multiplied by sequence length, basically those H0 to H8. We put them all on the same bag, all 8 across all the examples in our batch of 100. Actually, my batch size here is, I didn't put it. So just with this reshape operation, we can now add a perfectly normal softmax activation layer. So again, I'm using the layers interface to define it. Linear defines behind the scenes a weights matrix and a bias vector and does the weighted sums. And then I feed this through my softmax activation function. And this will treat all of those H to Y transitions as, one little cell. And it will process more of them because some of them come from the batch examples, some of them come from the fact that the cell is iterated, but it doesn't make any difference. It will produce all of my outputs like that. So that was a long explanation to say that there is a simple trick for defining the softmax activation layer, reusing the same weights and bias matrix in each of those yellow circles. And now I can also, now that I have my predictions, I can compute my loss because I know what I want to have on my outputs. That was the goal. Now that I have a loss function, I'm ready to train. Still a bit of shenanigans with the inputs and outputs. So this is, for example, what we want to put on the inputs, what we want to put on the outputs. Let's look at the sizes. So the input characters, I will have a number of those sequences in a batch, and each sequence is of length, sequence length. My x's are the one-hot encoded equivalents of those characters. So again, I will have a certain sequence length, number of them in a sequence, and each one of them is a vector of alpha size elements. That's for the one-hot encoding. My internal state, how big is this internal state? Well, batch size is the first dimension, of course, and those ages are of size cell size, that's the internal size of the cell. I have 3 of them because I have stacked 3 cells, so it's cell size multiplied by the number of layers. Now that we have all those, in recurrent neural networks, it's as complex to understand conceptually what they do as to actually feed them data correctly because there are so many inputs and outputs without making mistakes. So now I'm ready to align all my inputs and outputs correctly. So those are my inputs, the input sequence, which I one-hot encode. So now it's a sequence. Each vector is of size alpha size. My placeholders for my outputs encoded in, let's say, ASCII and encoding in one-hot. My internal state, we've seen that its size is cell size multiplied by the number of layers. Now I write my model. From the predictions of my model, I apply argmax, which in a vector of probabilities tells me which which element is the biggest one, and returns the index of that element. So that is what goes from one-hot encoding back to ASCII or numerical encoding of the characters. And the outputs of my model, I did this little trick of putting all the batch examples and all the examples coming from the different unroll steps in the same bag. So that's why I have a batch size multiplied by sequence length there. So now I need to reshape it to get back to batch size, comma, sequence length, a nice matrix when I have in this matrix on each line one sequence of predicted characters, on the next line the next sequence of predicted characters for the next element in the batch. And I can have my train step where I ask to minimize the loss. All right, am I finished with all the problems? Well, no, I'm not. Now I need to batch this information correctly. So let's consider the first batch of sequences. I have a text, and I extract 30 character sequences from it. Let's say the first sequence is the quick Okay, so this will be inputs on my recurrent neural networks unrolled here 8 times. The next batch, the next line. Can I continue the sentence, the quick, which is probably the brown fox, can I continue it on the next line? Well, no, I can't. Because I need to pass the output state, which I obtained when I fed in the quick. I need to pass that into where I ask it to process the continuation of the quick something. So actually, here is how the second batch has to look like. And the sentence has to continue across the first line of those batches. And into the third batch, and so on. Because the internal state is passed from iteration to iteration like that. Which means that on the second line in all the batches, I will be using sequences from way further down in my example, in my sample text. How further down? Well, it's a simple equation to write to exhaust all your inputs, so we'll not get into it. But that's what you have to remember. To correctly batch these examples, the first sequence has to continue as the first example in the second batch. It has to continue as the first example in the third batch, and so on, because that's the direction in which the internal states are passed. By the way, there is a utility function somewhere in the examples that does this slightly complicated batching. Just use it. Someone already wrote it. So here's the full code of this language model. So let's recap. We have a placeholder for our input sequences, our desired output sequences, and a placeholder for the state that we will be passing around. We have our model, which is our GRU cell, replicated 3 times deep, replicated 30 times wide. Then we have this softmax output layer, which transforms the results that our RNN cells are giving us into probabilities for characters, the loss and the training step, and the training loop, in which we are loading our sequences in batches using this slightly complicated way of batching things. So, we are ready to train this. And actually, I'm going to train this on the complete works of Shakespeare. And once I do this, well, what I'm going to do is that I will take one of those cells, just one, okay? It's trained to receive inputs and produce a probability for output characters. So I will just use that one cell and use it to generate text. On the fully trained network, I will take one cell, I will input garbage. It will give me a prediction probability for the outputs. So I will roll the dice and select something from those probabilities, which I put back as the input, and by repeating this, I get text. So I actually did that, and what I'm going to show you is this network. Sorry, this card and this card. What I'm going to show you is I saved checkpoints as I was training, so I'm going to reload some of those checkpoints and show you at different times in the training what this network is capable of generating as text. All right. What did I do? Now this one is correct. This one go away. And RNN play. C2 and here let's say like this. run, and run. Run. So, not trained a lot. It picked up the fact that it should be using paragraphs and words, but yeah, that's not so great. Let's try something that is a bit more trained. So let's go for C4. Now I trained it for a lot more. I think it's like half the corpus. Oh, look, it looks like a play. It's still not completely English, but it picked up the fact that there are supposed to be character names in all capitals, and then that they were supposed to talk for a certain amount of time, and then a new character should talk. So this is much better, and it's not yet very, very good at English. So let's train it a little bit more. Let's see here, C6, for instance. Oh, now we have a long monologue, and look at it. The character names are actually quite credible. Prince Anthony, Cleopatra, Cetus, Clown. It even picked up the fact that when the character is not a name, but a function, like a clown or servant or something, it has to be capitalized differently. Queen Antigillus. I can guarantee there is no Queen Antigillus in Shakespeare. This is a hallucinated name. But come on, if I didn't tell you, would you have picked that up? Those hallucinated names are actually very credible. And look, it's starting to speak English, which is correct. This is correct. It's starting character by character to learn how to spell English. So let's try with the fully trained network now and see if we can generate a Shakespeare play. So Shakespeare B10. And here I have to change this to 2. All right. Well, this looks like a very credible play to me. Look, I have scenic indications. I have exit, re-enter Mark Antony and Burgundy and Columnius. I have Marcius. This is actually English. This is my father from my sing and yours, the Senate and the best of this same spirit. What is the matter with me, sir? So, come on, who would like to play hallucinated Shakespeare with me? I need one character. I need someone. Please, come on, come here. Who wants to play Shakespeare? Yes, Shakespeare. So you will be Marcius, and I'm the second watchman. Now, actually, we already did Marcius. Let's try something else. Juliet. You want to be Juliet? Yes, why not? So you be Juliet. Please do Juliet, and position yourself. You're Juliet. Please play the role, and I'll position myself here. We do some scenic indication, like here. This is for wisdom effect. This is for dramatic effect. Let's go. We're ready.
Told the soldiers that I should not lose the sea.
Have with your hands. My liege should break it to your lordship. We all go out. The man is mute, my lord, and you shall not be made. That what your lordship show me not. Enter a messenger. You play the messenger now.
Hello, I'm a sorceress.
Romeo, a most precedent of this, and seek out of the Senate. Thank you very much. You've been a wonderful Juliet. Thank you so much. All right. So I hope I've shown you how to build a recurrent neural network, and also that these guys can be quite powerful at doing various things with mostly language processing. Actually, I also did the same thing on the TensorFlow Python code, and this is what I had in the beginning. It doesn't look like code. This looks a lot more than like code. It picked up the keywords already. Then it learned how to use the keywords correctly, with def and a colon at the end and a function name in the middle. It's still getting the parentheses a bit wrong. But then in the end, it can actually recite the Apache license completely. it can actually, close and open parentheses completely, and it can give you TensorFlow tips. Look, it figured out how to make comments. So create the string operation to apply gradient terms that also batch. It's very important. The original of any operation as a code, when we should always infer to the session case. Yes, we should always infer to the session case. I please you remember that. We should always infer to the session case. Makes sense, doesn't it? All right. The guy who originally built this language model also tried it on LaTeX. He took a mathematics book and trained it on LaTeX. It produced almost functional LaTeX. He had to fix it a little bit to make it compile, but when it compiles, well, it's a credible, mathematics book. It even tried to make, a drawing. It even tried to make a proof. Look at the first line, proof, omitted. Oh yeah, that's a good proof. So, there are a lot more things that you can do with recurrent neural networks. Character-based, word-based. You can feed words once you know how to embed words into vectors. You can predict sentiment. You can predict categories. And that is also actually how text translation works. You input a sentence in a given language, and you train the network to output a sentence in another language. And finally, have you heard about text labeling? Image labeling? Well, that's a recurrent neural network. You train it on an you train it on characters which are produced from the desired output sequence. You just add more information, which is some information from an image, and you obtain an image captioning neural network that can say things like this: a herd of elephants, a person riding a motorcycle, that's fantastic, or like this, a yellow school bus or a refrigerator, whatever. Well, there is still room for improvement there. Thank you very much. And by the way, if you want to use this stuff, CloudML, very nice. We just launched a whole infrastructure for running your TensorFlow neural networks on Google's cloud. If you don't have 500 of those GPUs under your desk, you use CloudML. And the session is open for questions, or you can just come and see me afterwards. Yes?
DeepMind of Google
Yeah.
put out a paper in Nature last month about differentiable neural computing that uses recurrent neural networks. And I just wondered if, in layman's terms, if you could explain what that is.
I'm not sure I know which paper you're referring to, but is it the paper that is, they use a recurrent neural network to produce neural network architectures?
It has its own memory, so it has read and write heads into memory.
So maybe it's not that one. The one I have seen is that you see here we have used different neural network architectures, like 3 convolutional layers, 2 fully connected layers, or 5 fully connected layers, and so on. So they figured out a way of actually generating that, because it's just a sequence of symbols, like convolutional, dense. It's just a sequence of symbols. So they applied a recurrent neural network to generate this sequence of symbols, and they have a neural network generating the ideal solution for a given problem, the ideal neural network shape for a given problem, which is kind of neat. Other questions? Yeah? Of course, yeah. We have seen both in the low-level API, there is the conv2d function that will just scan an image in 2 directions, or in the higher-level layers API of tf.learn, you have a layer.conv2d layer, which is a convolutional layer, and which defines its internally its weights and biases correctly. So yes, convolutional networks are well covered, and they are fairly easy to cover. What I really like is the API they put together for recurrent neural networks. That one is really clever. All right, well, thank you for your 3 hours of attention. I really appreciate you staying here with me for so long. And I'm still around. I will be around for a couple more days, so feel free to come and talk. Thank you.